Okay, I can see we just hit 1 minute after the hour, so I'm going to go ahead and get things started. Thank you for joining. My name is Matt Thomas, and you're tuned into the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone or video camera. And we're going to wait until the end of today's presentation to take questions. So in the meantime, if you're not intending to speak, please do the best you can to make sure your microphone is muted and your video camera is off. It's my pleasure today to introduce Matthew Morris. He is a mapping geologist at the Utah Geological Survey, and he's working on a broad array of projects around the state. His background is in geomorphology, and he has 2.5 years experience at the USGS Utah Water Science Center, as well as a PhD from the University of Oregon. He's actively engaged in the research of rock glaciers throughout Utah and the Intermountain West, which is partly what prompted the study you're going to learn about today. Matthew, thank you so much for joining us. I'll go ahead and let you take it away.
Awesome. Thank you so much, Matt. And just to confirm, you can still hear me pretty well?
Yes, I can hear you perfectly.
Okay, awesome. And thank you for the introduction, and thank you all for coming today. I see some familiar names in the attendees and some former colleagues from my federal days, and a lot of names I don't recognize. So I appreciate all of y'all's time today. As Matt said, I have a earnest interest in rock glaciers, which sort of precipitated most of this study or some of this study. But today we'll be talking mostly about a landslide, less about rock glaciers. And specifically, we'll be talking about a landslide that took place on June 28th, 2022 in Chaos Canyon in Colorado. And I want to just highlight my co-authors, all pictured here. Thank you everybody who has a headshot on their websites. It's very helpful. But they are not able to, most of them aren't able to attend today, but I couldn't have done this research without a really capable team. And with that, we're going to get started. What I'm talking about today is summarized in this paper, which was published last year in Earth Surface Dynamics. And if you want more information about the study beyond our discussions, I highly recommend you check out the study or the paper as a primary source, but also take a look at a companion piece or a second study published out of the USGS, Geologic Hazard Science Center, by first author Kate Alstad. Both of these papers touch on the same landslide and take slightly different approaches to really reach some similar conclusions. I also want to say that as the list of institutions might show you, I had the real luck of having a diverse set of colleagues on this paper, but also people who really like to accumulate different affiliations. So if you have more than 2 affiliations, like maybe try to pare that down a little bit. And with that, we'll get started. So we're going to talk about specifically a place in the Western US. So we're going to start with this map down here. If you're unfamiliar with the lower 48, we're going to zoom into Colorado. And if you've ever been to Colorado, you probably flew into DIA, which is like way over here. But Denver is the capital of Colorado. And we're going to look here in the northern Rocky Mountains, where Rocky Mountain National Park is, which is highlighted in this figure. Here's the park boundary. And within Rocky Mountain National Park, we're going to take a look at a single catchment called Chaos Canyon, which is located sort of south central in the park. That canyon runs roughly east-west or north-northeast, south-southwest. At the bottom of the canyon is Lake Hiaha. This is a very popular hiking destination. And at the top of the canyon is Hallett Peak and Otis Peak. These are 2 taller mountains right on the continental divide between Pacific and Atlantic draining river systems. And in black here is the feature we're going to be talking about. This is prior to the landslide taking place. So this is the the semi-stable non-collapsed landform. Prior to collapse, I should say, prior to 2022, LIDAR is the base here. So with that sort of geography, we're going to now launch into the story of this landslide. And really, it's a story of social media because we live in an age when everybody has a camera. And this is actually a video taken by a hiker at Lake Hiaha on June 28th. So he zooms in a little bit, and we'll watch this a couple times. So you can see there was this large deposit that was translated down slope, and it's mostly obscured by dust at this point. Let's go back and we'll watch it one more time. A little bit more narration here. You'll see these large blocks. I'll be referencing this several times. The Alstad study, they call these the two towers. They were two large boulders on the very front of the landslide that translated almost to the toe of the landslide deposit as well. You can see the material continuing to evacuate sort of up here by the headscarp of the landslide. But most of what's happening is very much obscured by dust, but still pretty phenomenal to be out on a hike and see a landslide just out in the mountains. If we were to go now into the future, 10 days post landslide, this is what we would see. So I took this picture on Otis Peak, which is to the south of the landslide. And you can see the deposit here sort of draping the landscape. There are those two big boulders that I mentioned, the two towers. The snow here is a nice reference for how the deposit spread out as it went down. And there's a little bit of a debris channel here that's still quite wet. A little bit of snow up here, and then you can see the area that was evacuated by the landslide as well as the headscarp just below the summit of Hallett Peak. And this is quite a popular hiking destination. So quite a few people may have been up here, and who knows if they were even aware that there was a landslide taking place. And this is all to say, this is a little bit of background. So I was actually sent that video that was posted on Twitter by a friend and USGS colleague, who I don't know if he's in attendance, but he knows who he is. And that really started sort of the process of building a team of scientists who were interested in looking at this landslide. And with and sort of the idea of we all had varied interests, but also varied skill sets. And really one of the themes through this talk is that you really want to think about not just who is the dream team, but really who are the scientists that can help you accomplish a scientific study and actually answer questions about a phenomenon. And I was very lucky that these scientists, I mostly got connected to them through social media and through, unfortunately, the now deceased social media Twitter. May it rest in peace. But very quickly after this landslide was posted on social media, I was messaging with other scientists who I'll mention in a moment. And we were able to organize different field campaigns and take our conversations off of Twitter to email. And that brought in other colleagues who were collaborators of theirs. It really started in the social media sphere, but also started as a collaborative project from the get-go, which I really appreciated. And really having motivated peers and colleagues was very helpful for this. But within 48 hours of the landslide, getting that video, I was actually able to make plans to go to Lake Hayaha with a USGS colleague, Tim Weinman, who at the time was part of a long-term monitoring project at the Loch Vale, run out of Colorado State and the USGS. So we had made plans to get on site very quickly. Still in the outside the exclusion zone, the park closed that whole area because of the rockfall hazard. And then within 3 days after the landslide, I was actively emailing with Bree Rick, who was a grad student at CSU, and she put me in touch with Ben Lehman, who's a postdoc at CU at the time. And we were able to build a conversation about, well, what observations should we make if we do go in the field? And then very quickly, within 10 days of the landslide, we actually wrapped up all the field work that we could do. I was there visiting family. Ben and Benjamin, their postdocs wrapped up, and Bree moved on from CSU. So very quickly, we got the ball rolling, and this paper is based on only maybe 2 days of field work and a lot of remote sensing data. And I'll talk more about the timeline of how we built this study at the very end. Just a bit more of LIDAR, because as geomorphologists, we all love LIDAR. As Gordon Grant would say, LIDAR is crack for geomorphologists. I think I can say that in this context. But here's Lake Hayaha. So this is where a lot of people go hiking, and that video was shot from here looking up the catchment. This is the pre-failure LIDAR. So this is the landform that collapses. And one thing I'll note is there's a lot of big boulders in this canyon. It's called Chaos Canyon because of some of the massive deposits that you find in there and how bouldery and rocky it is. And another point about these rocks is they attract a lot of people. And if you ask what's so important about Chaos Canyon, well, it turns out it's the boulders in the sense of human traffic. So there's a very famous boulder problem. If you're not familiar, bouldering is climbing without a rope on a small piece of a mountain or a big boulder. There's a very famous boulder problem here called Jade that attracts people from around the world. And then this boulder up here is called the Colossal Boulder, and it attracts climbers as well in this zone that was called the upper chaos prior to the landslide. This is now all closed to climbers, at least at the uppermost extent. And that's another question of hazard is you have a lot of people going into this canyon and spending time under this landform before it collapses. A little bit of geologic context here. We have a geologic map that was made some time ago and digitized in the early 2000s, but the landform again is highlighted here prior to failure, and it sits on the contact between the silver plume granite, which is this sort of orangey yellowish unit, and this purplish unit, which is a biotite schist. And not only is it on the contact between the two units, but the biotite schist has a adverse dip, so it has a foliation dipping into the canyon, which could contribute to some of the failure. We'll talk about whether there was basal sliding in a moment, and whether or not that landslide actually failed along a bedrock surface in its upper portions. Most of the rest of the catchment is mapped as QR or rock glacier. There may be some actual rock glacier down in the lower portions, but a lot of this is landslide or QT talus, so large boulders. And I initially got interested in this phenomenon because I'm studying rock glaciers, and I was curious if this landform that fails might have been a rock glacier that collapsed. They have been observed to do that in the Alps, but there haven't been a lot of observations in the US of such features. A bit more imagery. So this is Hallett Peak here, and this is Otis Peak, where I took that picture looking to the north. This is pre-failure. So here's the landform that fails. And I'm just giving you a lot of background on what things look like, because we're not going to see a lot of imagery through the rest of the talk. But prior to failure and now post-failure. So again, you can see through this perspective image, the landslide deposit spreads out. There's actually some of the finer grain material makes it all the way to the bottom of the canyon. Go back and then go forward. And let's do that one more time. It's pretty fun. And then moving forward again, we see this area has been evacuated with lots of the debris moving downslope. There's a little tarn here that turns bright blue. Another phenomenon that we didn't dive into is the downstream effects of rock flour from this landslide. And I had conversations with Jill Barron and others about that, but we didn't get the study rolling. But there are lots of questions that could come out of this landslide that we didn't address. And I mentioned we were able to get into the field rather quickly. So within less than a week, just about a week of the landslide, I was able to go with Tim Weinman to Lake Haiaha and take a couple of pictures. This is just above Lake Haiaha, and you can see the landslide here sort of spreading out, and you can see all the way up to the headscarp in the area that was evacuated and is still dark and with water coming from that melting snow, and some dark patches, which I'll talk about in later in the talk as well. And then 3 days later, Ben Kampforts and Ben Lehman, both postdocs at CU Boulder, revisited this site and then continued on to Mount Otis and took perspective views of the landslide, which they're going to integrate into a structure from motion model. So they were able to take convergent photos of the landform, and those will be used for our volume estimates. But again, amazing exposures, great weather, and they were able to take a lot of very good photos that helped build that model. But I should also add, this isn't the end of activity. It wasn't just a single collapse, but there's actually a debris channel here on the side of the landslide that continued to be active throughout at least the time period we were making observations. And then even 7 days later, when the next USGS team was able to make a survey with a small unmanned aerial vehicle. And one of the ways that activity was noticed was through just some videos that I was able to take from Mount Otis looking at the landslide. We were able to observe some of these debris flows. So there's still a lot of activity. This is maybe mixed fine grained sediment and snow, but it contributed a lot of material still moving down the slope. So the park had this whole canyon closed for almost a year until the USGS study came out to show sort of what was the hazard. But you can see there's still a lot of things coming down the slope that could be dangerous to climbers. And actually there were climbers down off screen when the landslide took place, and they were very good at taking videos of the landslide and not running for their lives, but they survived. Ben Lehman put together this geomorphic map of the landslide based off of his initial visit with Ben Kampforts, showing the landslide deposit spreads out as it gets lower elevation. There's still some unstable rocks and neve up higher, as well as a lot of running water up here in sort of the headscarp region, and then that debris channel off on the side. So still an active landscape, but we were really starting to collect observations we could use for a study at this point. So within 10 days, we had some field observations, and that got conversations going towards what do we actually want to research here, which maybe is backwards from how a lot of us think about science, but was opportunistic data gathering, I would say. And also just a wider shot, again, here's the landslide. Lake Haiaha also had a similar effect downstream where the rock flour gave it this beautiful teal color or aquamarine almost, and that's unusual for that lake. A closer shot here, it was stunningly beautiful, and the next summer there was actually still some amount of rock flour. So if anybody has access to the data or could talk to Jill Barron or is interested in studying this, give her a call, and I think there's still samples from that summer. And with that, we collected some data, and I was able to collect also some people who were keen to study this phenomenon and understand this landslide. And that really launched a series of questions. I'm somewhat weak at the hypothesis-based science game, to my PhD committee's chagrin or frustration. So rather than hypotheses, we started with questions, which were, first off, was this landslide moving prior to it collapse on June 28th? Was it moving slowly and then accelerated to collapse, or was it spontaneous in collapsing? What were the climatic trends that led to this collapse? Was there we know there's a broad warming across North America, but was there a distinct acceleration in warming, acceleration of snowmelt that may have contributed, or what else could be going on in terms of climate trends? And then also we have this photogrammetry data set. Can we constrain the volume of the slide? How does that volume compare to other landslides? And since we have its run out distance and volume, we might be able to say something about its mobility. Irina Overeem took on the task of modeling whether or not permafrost might have been present. I mentioned it had some similarities to a rock glacier. Well, let's actually try to test whether there might have been internal ice in the landform. And then also my colleague Leif Anderson, who's at the University of Utah, he actually took on the task of making a 3D model, or 2D model rather, of the landslide and trying to test its stability as a landform prior to collapse and test whether or not the rheology of the landform would change with introduction of snowmelt or other changing boundary conditions. And then sort of a final story that we all tried to answer was, what does this work that we've brought together tell us about other alpine landforms and their stability in a warming climate? And I forgot to call people out by name, but on the movement side, Quinn Brencher, Al Handwerker, and Jeff Moore were very active. I was working with Bree, Rick, and Leif on the climatic side, Ben and Benjamin on the volume side, Irina Overeem on permafrost modeling, Leif on the 2D modeling, and then all of us contributed to the discussion here. And so I'm going to walk through in my talk each of these questions and how we address them, and hopefully provide some convincing evidence. We'll see. But first question, was it moving prior to collapse? Luckily, there's really good Planet Labs imagery of this area for years preceding the landslide. I'm just going to show you a quick GIF here. So keep your eye on the landform right here. And then you see the landslide collapse. Let's run that one more time, since we have the time. And you might notice these are those big boulders, and you can actually see them creeping down slope. And we'll get to rates in a moment, but it appears based off this imagery, we can answer the question right away. The landslide was moving prior to its catastrophic collapse, but we really want to understand how quickly was it moving. And we chose two different methods to approach this question, both InSAR, so interferometric synthetic aperture radar, and then also a technique known as pixel tracking. And Quinn and Al led the InSAR charge here. And that's a technique I'm going to describe a little bit in detail for those who are unfamiliar. And then pixel tracking we'll get to, but it's a little bit more intuitive than InSAR. But basically, and I know there's some InSAR experts in the audience, so forgive me if I am not an expert, but we have a series of satellites that are circling the Earth, and they are scanning the Earth's surface with radar, or radar near wavelengths, and measuring that distance between the satellite and the surface of the Earth. If there's any deformation to the surface of the Earth, be it, in this case, an earthquake, for instance, or a landslide, and that distance from the satellite and the surface of the Earth changes, What you'll notice with your instruments is that there's been a phase shift. So your nice sinusoidal wave that you were getting is offset to some extent. And it's the phase shift that becomes important for InSAR. And if you were to look at two different frames of InSAR, so for instance, here's it looks like static right here, but two different frames from August and then September, and thank you to Gareth Fooning for all these slides, you'll find that there has been a phase shift if the surface is deformed. And that you combine those two images into what's called a wrapped interferogram. And that's the InSAR images that we're probably familiar with, were these fringes that tell you about deformation, but it's not true offset, either in horizontal and vertical space or even line of sight. To do that, you have to unwrap your interferogram, which I won't get to today in detail. But another concern with InSAR is that you have a satellite. That satellite is orbiting the Earth, so you could think of the satellite coming over the horizon in an ascending path and then descending behind the horizon. So you get two passes at the same landform. And what you're measuring is the line of sight distance to the landform. So the velocity you're going to get at least initially is a line of sight velocity. So that's what I'm going to mention today, is only LOS velocities. But another concern with InSAR is your satellite only can look in a straight line down at the surface. So there are areas where you could have shadowing. So if you have a large cirque wall, or if the angles are just right, the satellite won't see the surface of the Earth very well. This was initially a concern for this landform, but we found it was actually not shadowed and well resolved, at least with InSAR coverage. We'll see about the results in a moment. But again, keep line of sight velocities in mind. So first, what Al and Quinn put together was a wrapped interferogram. So this is just looking in phase space. And this is the area of interest here and the area where the collapse took place. And what you'll notice is there's a lot of variability in the phase. You don't see a distinct continuous phase direction, unlike this landform up here, which is a bit more consistent. This is a rock glacier. And consistency would indicate that the landform is moving away from you in the same direction. And there's a lot of noise basically in our landslide. And that shows up even when we do line of sight velocity. This is even more apparent. So there's a little bit of red and blue pixels in our landslide, whereas this rock glacier is almost entirely red, which is motion away from the satellite. If we just take a look at the variance of velocity, we'll get a standard deviation within the landslide, and you'll notice our landslide's a little brighter or darker in green, which means more variance. And that also means the signal is less consistent. So it's a noisier signal, less of a coherent body moving away from the satellite. And then another measure of how coherent are our interferograms is very low. So these very translucent blue colors means this whole area is actually poorly resolved by InSAR. And we tried a bunch of, or I should say, they tried a bunch of different ascending tracks, 2 ascending tracks and 1 descending track. And across line of sight velocity, that standard deviation measure, and coherence, found very low reliability. The InSAR method doesn't seem to be producing a very strong result for us. And one thing that's really interesting about that is we have good coverage. The satellite sees the whole landform. But again, we're looking at the offset of not necessarily just a sine wave, but of a wave. And if we moved more than a wavelength or more than 2 wavelengths, your InSAR method is not going to be able to detect movement. And so what we concluded is that the rates of deformation for this landslide were simply too high for accurate unwrapping. So we couldn't measure velocities accurately because the landslide was moving too quickly. And in the case of the S1 or Sentinel-1 satellite, that would be if it's moving more than 2.8 centimeters over a 12-day period. So we already know something about the rate of deformation, at least a minimum, based off of this poor resolution. And if we return though, so this was sort of a like frustrating result. We didn't get a good result from InSAR. But if we return to this image, I showed you that Planet Labs actually did a really good job of tracking the landslide. And what we can do is take a look at all of the pixels in the Planet Labs imagery and use those to calculate velocities. So this was taken on by Jeff Moore and Al Handwerger, and they tried 2 different techniques. They used the Planet Labs imagery, and actually Jeff used Google Earth imagery. So that Maxar imagery that Google purchases is really, really good, sub-meter resolution on a lot of the pixels. So he looked at 2 pairs of images, 2016 to 2019. Here's our landform that collapses, and found that in that 3-year period, some of these pixels are moving almost 10 meters in terms of their horizontal offset, which is really fast. And in addition to just measuring their bulk offset, he was able to create a vector diagram of velocities and show that not only is the top of the landform moving, but it appears that the bottom of this slope is also displacing, which is important because that tells you about your mechanism of movement, whether or not you have some amount of actually basal sliding, so the landslide sliding along its base, deforming the bottom of the front, or if it's just internal deformation. That would seem like an important observation just based off this result. And then Al was able to come in with the Planet Labs imagery and actually measure displacement per year. So going back to mid-2017, showing that each year we're accumulating in the landslide significant displacement. And for reference, here's a stable slope, which is not moving, thankfully. And then convert that to velocity. So we're getting velocities of 2 meters a year in 2017, and it accelerates after 2019 to almost 17 meters a year. So this thing is moving very quickly. It's not surprising we don't see the InSAR at resolving this because we have such a rapid rate of movement. But it's, you could almost sit there and watch this thing move, it feels like. And another nice thing about this result is it pairs really well with the Alstad 2023 study. They showed a very similar trend in terms of both displacement and velocity, really accelerating 2018, 2019. So to bring it back to our questions, was the landslide moving prior to collapse? It was, and we can actually say it was accelerating. And for those familiar with landslides, you could do a 1 over velocity calculation and try and see if that helps predict the failure. And it's reasonably close, like within a few months, I think. But exciting to show that it was moving. Nobody really knew or was aware that it was moving, and then it collapsed. And then what can we say about the climatic trends leading into collapse is our next question. So luckily, we're in Rocky Mountain National Park, where there were lots of weather stations close by. So Bear Lake has a big trailhead, but also has a snow-tell site. And then the Loch Vale is a long-term climate monitoring site run by Jill Barron. And they've had climate station data since the 90s there, as well as outflow and lots of geochemistry. And these are within just a couple of kilometers of the site. Here's the landslide. So we were actually able to take the data from these sites, and then I constructed a local lapse rate using a site in Estes Park, and then adjust the temperatures as if we were at the site of the landslide, and look at what are the temperature trends through time. And so these next two plots are kind of our summary of that analysis. The top plot here is temperature as days of the year. So January 1 is 0, and then end of December over here. And this is just the temperatures throughout the year at the landslide, and all roughly 30 years of records. This goes back to early 1990. All of the gray lines are all of those years, and the blue line is 2022. And then this is the date of the collapse. And this is just to highlight that 2022 didn't have significantly warmer temperatures than all of the previous years. It's sort of in the middle, to be honest, on temperatures. There are some extrema in here, but not a lot. And if you do a more detailed analysis, again, it's pretty much average with the 30-year record, or like slightly warmer, but not significantly warmer. And then with the temperatures, we were able to actually convert that to a ablation rate, or the cumulative amount of snowmelt. So that's what's shown down here is cumulative snowmelt starting at April 1, sort of our arbitrary cutoff for spring when the snowmelt begins, and showing you those same records going up to June, just past June 28th. And again, in blue is 2022. And what we want to highlight here is that 2022, in terms of snowmelt, the rate isn't crazy fast. It's in the middle of the pack. 21 and 18 were both, and 20 were both more rapid snowmelt years with a faster ramp up and a higher amount of snowmelt by this time. So again, there's not a huge like red flag of, oh, it was a huge snowmelt year, it was really warm. None of those factors seem to apply. But again, we are also on the end of this ramp. So we're at or just past peak snowmelt. So there is a lot of water in the system, and maybe that's relevant for the cause of the landslide. which we'll get to in a moment. And then I just want to show you that this is backed up by our Planet Labs imagery. So each of these numbers here is a frame over in this figure, showing you that in frame 1, we have still a lot of snow on the ground, but as we get down into frame 3 and 4 and 5, just post-slide, there's a rapid melt-off. So we really feel confident in these numbers showing us a trend in snowmelt. So we at least know from this climate analysis that it appears the landslide took place at or just after peak snowmelt in this area. And in addition to the snowmelt story, we were wondering about, well, what is all this water doing to our landslide or the landform as it fails or prior to failure? And this is what Leif Anderson took on, is can we use any modeling to evaluate the rheology of the slide to gain insights into these processes? And so Leif was able to put together a 2D model using a software called Slide 2 or Slide 2D, I believe. And he constructed a 3D model first of the landslide and then cut a slice right through the middle of it and constructed this more simple 2D model and looked at the factor of safety of the landform prior to failure. And he found that if you didn't include any effects of snowmelt, the factor of safety was slightly greater than 1, so meaning it was not likely to fail. But with the introduction of even a little bit of groundwater, so raising that water table even by a meter, the factor of safety drops to less than 1 and your landform fails. This really keyed us into the idea that groundwater and the surface water going into the landform was important, which we'll touch on how the water actually gets into the landform in just a moment. But thinking about the fact it's moving, that could be opening cracks that provide more avenues and flow paths, both into the landform and then maybe to that basal surface. So I mentioned early on that there's an adverse dip or a foliation. So this is above the landform looking down. And there's a pretty nice exposed bedrock shear face here that the landform was buttressed up against. And so if you can get water on that, that could be another mobilizing agent for this landform. But what we weren't sure about is or I should say, was there any ice inside the landform? Because if it's a rock glacier, we know those are somewhat inhibitory to actually getting water into the landform. It hits the ice and runs off rather than percolating through the landform. And so an active question was there actually permafrost in this landform before it failed? And is there any evidence for degradation of permafrost through time? The idea being, as you melt permafrost and it becomes more spotty, you can actually get more water into that landform and help it fail. So Irina Overeem did some permafrost modeling for this work, and so she was using the GIPL model, which is from I think University of Alaska Fairbanks, using the same climate data that I used for the climate analysis. She was able to show that after about 2 meters of depth, you stabilize your temperatures at below 0 in this landform that collapses. And across a whole water year, I should say, you see maybe about 2 meters of penetration from the actual warming during the summer. But below that, you're going to have maintain a stable below 0 average temperature, which provides at least the conditions for permafrost. It doesn't mean there is permafrost for sure, but there may have been internal ice just based off of this modeling. And what's really cool is we didn't put this together in our study, but I'm going to reference Alstad 2023 here. They were able to show with some observational results. So they were there July 15th, so 5 days after our last day in the field. They were able to actually get up in and below this landslide. And they noticed that this is a frame from a video from those climbers on the day of the landslide. They noticed, Alstad and others noticed that these boulders which were in the video, well, upon their visit the next month, were actually piles of debris. And so they called these mallards, or these are a periglacial feature of melted permafrost. Basically, you get a big block that looks like a rock, and then over time, now that it's exposed, it melts and all of the debris it's holding within falls apart. And in prepping for this talk, I actually went back to some of my photos that I should have referenced when we were writing the paper, and realized that I had similar pictures that showed, so this is from Lake Haiaha just a week after the landslide. And I mentioned these dark spots here. Well, I was able to take a few pictures of these while I was in the field. And if we zoom in on these dark spots are actually wet areas in the landslide. There is snow over here that's probably melting, but it's not creating these wet zones. So these areas are probably permafrost melting. And in fact, this one looks like a big diamicton or a big mixed grain size boulder, but it's being held together by a very dark, very wet matrix, which is probably permafrost. So again, an observational support for the idea of internal ice in this landform. Maybe not a classic rock glacier, but still an area that had ice internally, and perhaps the degradation of that internal ice helped facilitate its failure. I also was able to capture a different perspective on those little piles of debris before they had totally melted, which I think a week later, when the Alstad USGS group was there, these were just entirely cones of debris. So again, go back and look at your field notes or field photos, because there's more hiding in there than you think when you start your study. But again, very cool to have observational evidence of permafrost where our modeling showed there should have been permafrost. In addition to these observations, we wanted to understand how big was this landslide? Is it, in terms of size and scale, similar in mobility to other landslides that are well documented, or is it less mobile? Given the fact there's ice internally, we would have thought that could facilitate movement and maybe make for a more fluidized landform or landslide. But it looked very viscous. If you watch that video again, it sort of slides down the hill slowly. So not very fluidized. But what helped us make this possible was Ben Kampferts and Ben Lehman, and they went out and, as I mentioned, took photos from a bunch of sites on the ridge looking across at the landslide. And they were able to put together a structure from motion model. So again, they had these amazing positions just looking straight unopposed at the landslide. It's almost a perfect setup for that technique. And they put together this DEM of difference, showing that the area of erosion here, which had up to some of those peaks of those big boulders, had up to 45 meters of erosion. And then the area of deposition here on the downslope side with almost a matching 45 meters, up to 45 meters of deposition or slightly greater than. And this DEM of difference allowed us to calculate volumes. So in terms of volume of erosion, we had 1.3 million cubic meters, plus or minus 133,000. And then our deposition is slightly less, 1.2-ish million cubic meters, plus or minus 150,000. And the deposition might be just slightly off because of the how the deposits spread out, as well as the errors in the technique. And I'm not a landslide geologist, so these numbers don't mean a lot to me. But if we look at some plots and put them in the context of other people's work, let's first look at the landslide runout length versus the height in terms of how far it had to run out, and then volume. And our landslide plots just here, so we're on the well within the this red dot zone. This is debris and rock slides and avalanches, but we're lower on the mobility side. So this is also a measure of mobility. And actually our L over H, I think, is 1.8, so not very mobile in the grand scheme of things. And then if we look at volume of the landslide versus its planimetric area, it's, again, sort of in the middle of the field of all the slides, but on the lower end of the rock debris and rock avalanche slides. And actually another metric I won't show in a plot, but the area over volume raised to the 2/3 power is about 10, and 30 would be a high mobility landslide. And for reference, famous landslide Oso is just here. So much less mobile and smaller than Oso. And I know I'm just passing the 40-minute mark, Matt, but I'm going to keep going. We got a few more slides. And then the final question was, what does this work tell us about other alpine landforms and their stability in a warming climate? One of our main discussion figures is this one, which is the temperature record of the landslide going back into the 1990s. So here's average temperature throughout the year. The horizontal line is 0. And then looking at what is the actual annual temperature anomaly, noticing that after maybe the early aughts, every year is slightly warmer than the average. So again, we have a warming climate. This is definitely probably degrading the permafrost in the landform. Maybe that's allowing more snowmelt to percolate into the landform. And this is also backed up by, this is positive degree day sums, which is a measure of snowmelt. Just seeing that we're seeing accelerated snowmelts or more rapid snowmelts than we were in the early aughts and then 1990s. So potentially other landforms in similar positions could be at risk of becoming more unstable, or really we just need more monitoring because there's so many landforms like these that are not monitored at all. I mean, this is I think it was the 8th or 9th most visited national park, and there's a landform moving 17 meters a year and wasn't really under any observation or monitoring. And then it failed, and luckily nobody was hurt. But it really, I hope this drives home, like we need more attention to our mountains. As we've looked to the Alps as examples, there's a lot of monitoring of the Alps, a lot of interesting results in rockfall and increasing number of landslides, but we haven't noticed so much in our North American Cordillera the same increase, but that could also just be a lack of observation. And finally, this was our last figure in the paper, but I want to just give you a context for what a timeline is for a project like this. I know when I was a grad student, I was very uncertain of how long does it take to do science. And just to point out that the landslide took place on June 28th, and December 8th was when our paper was published. So, you know, in less than a year and a half, we were able to put this project together, which I really credit to having very motivated and really excellent co-authors. We spent 2 days in the field within a week, and then 10 days after the landslide. And then we gave a short talk at GSA that sort of brought together our initial observations. And then our paper was submitted April 5th. So if we really look at the timeline of what takes a long time for a science project, the writing and fieldwork is just over half. And then half of that time is peer review and revisions. So just for context, that took almost half of the project, but was still useful and very helpful. And with that, I will open it up for questions.